This is a class about the science of climate change, but I'm going to start by talking about the physics, chemistry, and biology of climate change. And the reason for that is twofold. First, if you want to solve a problem, you need to understand the problem. Now, most people know about climate change, and most people have an opinion about climate change, and that is no surprise because climate change has been prominently in the news for 3 or 4 decades now. But if you survey people as to what they actually know and understand about climate change, it turns out that that understanding is often faulty. And that is partly because what you can read in the so-called quality media like BBC or Guardian is often wrong. And also the material that is used in primary and secondary schools contains errors. And then of course what you hear in the pub or what you read on the internet goes even more wrong. On the internet you can read about climate change being a Chinese hoax, and you can read about how planet Earth would explode because of climate change. Now, none of that is even remotely true, but you can find any amount of nonsense. And even if the knowledge that is being conveyed is correct, then people may misunderstand it. I recall a conversation I had with my son, who was worried about what a schoolmate had told him about 5 meters of sea level rise, and I tried to reassure him saying, oh, this is going to be a long, long time in the future before sea level will have risen by 5 meters. And his reply was, so when I'm 14, 5 meters of sea level rise is really something that would occur in the second half of the millennium, and not in a few years' time. So the second reason why I start the way I do is just to get us all on the same page as to our understanding of the problem that we are trying to solve. The starting point is these 9 sets of observations. On the left, you're looking at the 3 most important anthropogenic greenhouse gases. That's carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O. And that is shown on 2 timescales from the start of the agricultural revolution some 12,000 years ago, and in the smaller inset from the start of the industrial revolution some 200 years ago. And what you see is that throughout most of history and parts of prehistory, the concentration of these greenhouse gases has been more or less flat, and then towards the end of the period you see these concentrations skyrocket. Now, that is a graphical illusion. If you look at the smaller insets, then what you see is that since the start of the Industrial Revolution, the concentrations of greenhouse gases has merely increased exponentially. Second set of observations is that the global mean surface air temperature has increased over the last 150 years or so. Average sea level has increased over the same period, and snow cover has declined. And this is a consistent set of observations. In order to understand that, we need to look at the natural greenhouse effect first, and then at the enhanced greenhouse effect. This is a cartoon of the greenhouse effect, now drawn to scale. This is planet Earth, and this is the Sun. The Sun is a big nuclear reactor in the sky, and it emits a lot of energy to outer space, and only a small fraction of that energy reaches us. And that energy comes in the form of radiation in the visible part of the spectrum, to humans, visible part of the spectrum. Some of that radiation is reflected at the top of the atmosphere, some of it is reflected by the Earth's surface, but most of it is absorbed by the planet. Now, that cannot be the end of the story. If the planet would just absorb energy and absorb energy and absorb energy, then the planet would have evaporated a long, long time ago, which obviously it didn't. So somehow planet Earth must get rid of this energy. Now, the ground does not lit up at night. If it does, you should reconsider your consumption of mushrooms. Instead, the planet emits energy in the infrared part of the spectrum, and it emits that in the direction of outer space, and that is this part of the graph. And that is where greenhouse gases come into play. Now, greenhouse gases are by definition gases, that's gaseous substances, but they're called greenhouse gases because the molecules of these gases are transparent to visible light, but opaque to infrared radiation. That is, if you take a CO2 molecule and you hit it with a ray of solar light, then that ray just passes through it as if the CO2 wasn't there. That same molecule of CO2, if it's hit by infrared radiation, it absorbs that energy. Now, that cannot be the end of the story. If a molecule absorbs energy, it gets excited, as a chemist would say, and if it just continues to absorb more and more energy, then the molecule would fall apart. That is not what happens. Instead, the molecule re-emits the energy it has absorbed, again in the infrared part of the spectrum, but it does so in a random direction. So the infrared radiation that is emitted by the planet goes in the direction of outer space, but only some of the infrared radiation that is emitted by CO2 molecules goes in the direction of outer space. Some of it is re-emitted back to Earth or into other parts of the atmosphere where it may hit other CO2 or other greenhouse gas molecules. So the implication of this is that because there are greenhouse gases in the atmosphere, it is easier for energy to enter the planet than to leave the planet. And as a result, more energy is stored on the planet, and that means that in equilibrium it is warmer. Of course, it is also true that on balance the amount of energy we emit as a planet is the same as the amount of energy that we absorb, but because of greenhouse gases in the atmosphere, more energy is stored on the planet and therefore it is warmer. And people have calculated that if there were no greenhouse gases in the atmosphere, then instead of the planet would be about 30 degrees colder than it is now. So the current average temperature is around 15 degrees. It would have been minus 15 had it not been for the greenhouse gases in the atmosphere. And that explains why this set of observations is consistent. So here we have the greenhouse gas concentrations again, CO2, methane, and nitrous oxide, and you can see that more of that stuff in the atmosphere, and that means that more energy would be stored on the planet, and therefore it would get warmer, and that is indeed what we have observed. This is true for the air over land, has increased. It's true for the air over water. No, it's true for air over water, that is this graph. It is true for the water itself, for the top layer of the oceans. And also if you go a little bit deeper into the ocean, you would see also an increase in the temperature, or rather in the heat content. It is true for the temperature higher up in the atmosphere. And all of that is perfectly consistent with there being more CO2 and other greenhouse gases in the atmosphere. Now, if air gets warmer, then it can contain more water vapor. And indeed, what we've seen is that humidity has also increased. Now, if air is warmer, then snow melts faster and more precipitation falls in the form of rain rather than snow. And we've indeed seen that the snow cover has decreased. If it's warmer, then you would expect ice to melt faster. We've indeed seen that ice on land has decreased and that ice on sea has decreased. And last but not least, if ice melts, then it turns into water, and you would expect sea level to go up. And of course, if water is warmer, it expands. And we've also seen the level of the sea go up. So this is a perfectly consistent set of observations. If the greenhouse effect keeps the planet warmer than it otherwise would have been, by 30 degrees or so. And if you enhance the greenhouse effect, if you put more greenhouse gases in the atmosphere, you would expect the place to get warmer, and that is what we have seen over the last 200 years or so.